All right, everybody, welcome back. I hope you had a refreshing lunch. We are very pleased to have Rob Stoke with us here today. Welcome, Rob.
It's great to be here. Thank you for having me.
All righty. I know I'm looking forward to seeing the latest updates from SLS and understanding where the super heavy lift launch vehicle of the day is is today. Rob has been a stalwart companion on his journey for the last 4 years. We've worked with him closely to understand what kind of capability NASA could bring to bear on a mission like this with this rocket. He has provided numerous analyses, multiple studies that they've done on their own to figure out how SLS can enable science, particularly for SLS probe, particular for the Interstellar probe. I just want to say thank you, Rob. Thank you to you and your team for making sure that when we needed the information, we needed to understand how this mission could shape up, you were able to provide it for us. Thank you.
I'm glad to be a part of it. Thank you.
And with that, the floor is yours. Kirby's going to run your slides, and welcome.
All right. Well, thank you, Michael. And originally, this was supposed to be presented by Dr. John Blevins. He's our chief engineer for SLS. He is currently down at the Cape in performing a miracle. He has been working 20-hour shifts trying to get this rocket off the ground. He's been involved in many of the tests that are involved in getting this rocket ready. They have shifts going around the clock. So, and he sends his sincerest apologies for not being able to be here. And so I'm here instead. I'm happy to be here. And thank you again, Michael. Thank you to the Interstellar Probe team. This is a wonderful mission to be a part of, and I'm sure we're going to set some records with this one. So next slide, please. So I'd like to say that where we left off with the last webinar, there was a webinar over the summer where I came forward and I discussed what we did with Green Run, the great successes that we had there, and also where we were with stacking and getting the vehicle ready for launch in the VAB. At the time, we had our boosters stacked and we had the core stage bolted to the boosters. And I think we're getting ready to bolt on the LVSA and the ICPS. And just so you know, we have boosters that produce about 3.5 million pounds of thrust each. And then the core stage itself produces about 2 million pounds of thrust. The boosters they don't have nearly as high ISP, about 255 seconds of ISP, and the core stage has one of the highest ISPs you can have for a chemical rocket at 455 seconds of ISP. ISP is a measure of efficiency for a rocket, and it really comes down to the momentum transfer of the rocket itself and the velocity of the propellant coming out the back. So with that, let's go on to the next slide, please. So where are we? Yes. Did somebody say anything?
Sorry, I was just making sure the slide updated. This is Kirby.
Yes, it finally updated on my end. Thank you. Okay, so where are we? Pardon? I'm sorry.
I'm sorry, please continue. I was just saying there may be a lag.
Yeah, there's a slight lag, but thank you. Okay, so what have we done over the last 3 months here? We've actually stacked the launch vehicle stage adapter. I have a video of that a little bit later. Also the interim cryogenic propulsion stage, which is the Delta cryogenic second stage for those who are familiar with the Delta rocket. We've installed many of our payloads in the Orion stage adapter. We originally planned on having 13, but we only have 10 installed. 3 of them couldn't make it, unfortunately. The Orion test, or the Orion stage adapter, we installed a test article on top with the Orion mass simulator to do a modal test, an integrated modal test. We did that for a reason. We wanted to allow for a little more time for our payloads, the secondary payloads, to be integrated into our flight OSA. And so that gave us a couple more months running room there. And we are currently running simulations around the clock, it seems. We recently did a wet dress or a cryo simulation just to make sure that all the things that need to happen when we actually load cryos onto the stage or on the vehicle go smoothly. So, and we also did an umbilical release retract test, and I have a video of that later. Can you go to the next slide, please? So I hope this plays properly. I have a video of the OSA, or not the OSA, the LVSA, the launch vehicle stage adapter being hoisted up into the rafters of the VAB and moved over onto the SLS. Hopefully it plays properly here. It looks like it's a little laggy.
Coming through though.
Okay. And just so you know, the LVSA, the launch vehicle stage adapter, was built by Teledyne Brown. It used many of the facilities at Marshall Space Flight Center to produce it, including the advanced welding facility where we stir friction welded the panels together. We applied the foam, the thermal protection system at Marshall, and a number of the components were installed there. And everything went smoothly with this stacking. Next slide, please. And I'm just waiting on the slide. The next thing to be stacked is the interim cryogenic propulsion stage. Like I said, it's a Delta cryogenic second stage that has been slightly modified to fly on this mission. There are a couple minor differences. We have a stretched LH2 tank along with a painting of the LH2 tank with our American flag right there. So it's a beautiful sight to see. This stage has been ready for years, and we recently had to take it back out of storage to be able to stack on the vehicle.
Rob, I just wanted to confirm that the video is indeed playing to make sure that we've had some problems with Zoom not updating PowerPoint. Did it play?
It's playing. It's a little laggy. You see bits and pieces of the video as it's moving along.
Okay, understood.
I see about a frame a second or so. That's what I'm seeing.
Coming through pretty well on this end too.
Okay. As you can see, you're hoisted up into the rafters of the VAB virtually and down onto the top of the LVSA. Keep in mind this vehicle is over 300 feet tall when fully stacked, and the launch pad that we're stacking on is about 100 feet in the air. So a lot of these operations are occurring close to 400 feet in the air in the VAB. It's amazing how small things appear. And that's a good example there where you see this very large stage down in the transfer aisle. All right, next slide, please. Okay, so in terms of our modal testing, before we put the core stage on the stack, so to speak, we performed a push-pull test of the SRB, and that allowed us to verify our models, both the stiffness of the booster and also of the pad itself. And then we did a full stack with I say full stack, but we had a structural test article of the Orion stage adapter along with a mass simulator for Orion on top of the vehicle. We performed a modal test. We don't have any very good videos of that. And the reason why I say that is that the vehicle itself only moves an inch or so, and it's very hard to see the motion for the integrated modal test. But I will assure you that the modal testing went very well. In fact, we were within 2% of our predictions, which was amazing, astounding. And also another piece of good news, we found that the core itself, the core stage, was a little stiffer than we had anticipated, which is what you want for flight. We're flying a very flexible rocket, and it will bend and flex. And we have designed the system to fly that way, where it will fly with flexible modes in mind. And we actually articulate our engines to make sure that we don't actuate or excite those modes in flight. So next slide. Okay, for umbilical release and retract, there's a lot of videos here. There's quite a few umbilicals that had to be pulled back from the vehicle. You can see the ones for forward skirt of the core stage and the LVSA here. Here's for the inner tank of the core stage, so between the LOX and hydrogen tank. And these went fairly smoothly. This is the aft service structure. There's umbilicals that reach over to the engine section. I believe this is where we load our cryos, and they pull back into a protective shroud. That's sort of neat. And here's another video of the inner tank umbilical separating. And here you can see our vehicle's stabilizer system dropping away along with the forward skirt umbilical for the core stage. We need a vehicle stabilization system on the pad due to the fact that the vehicle itself will move with the ground winds. And we designed to, I believe, 34 knot winds in mind. And if we go beyond that, we have to roll back typically. And you can see the ICPS umbilicals, most of those are pull umbilicals that pull back away from the vehicle, and then you see the arm move away to the side. And we also test the umbilicals for Orion. All right, next slide, please. Many of our CubeSats are installed. Like I said, we have 10 installed of the 13 that we originally planned to fly. Right here, you see pictures of Team Miles, Equalis of JAXA, Amatanashi, Lunar Ice Cube, and Nia Scout. And I believe there are 3 that couldn't make it, but oh, that moved on a little quicker.
Nope,
But
my cat.
okay, no worries. So the ones that didn't make it, I believe Lunar Flashlight was one of them, and we try to give them as much schedule as possible to get their payloads ready, but they just 3 of them just couldn't make it, unfortunately. Next slide. And I should mention that OSA is moving to the VAB next week. So we have only a day or so. If they were to miraculously show up, we could probably integrate them. Here is a picture of Charlie Blackwell Thompson on the left here. She's our flight director for Artemis 1. You can see her at her console performing a simulation. And we're doing many simulations to make sure that we get everything right come flight day, that there's no hangups on our side because we didn't do something right or didn't anticipate an operation going the way we had thought. So we're running a lot of nominal and off nominal simulations to make sure that no matter what the event happens, if it's predictable, we run through it and we know what to do when that happens. So next slide, please. We're making a lot of progress to Artemis 2. A lot of the hardware is already developed. In fact, the ICPS has already arrived at Cape Canaveral for the second flight. The Orion stage adapter, the welding's complete. I believe we're going to be I believe a lot of the closeouts of that stage adapter is being produced with the Artemis 3 stage adapter, and things are moving on very nicely. We're right on schedule there. The RS-25s for the second flight are already ready to go. They're actually hot backups for our current flight, so that's good. The LVSA for the second flight is already ready, and many of the components for core have already been produced and started integration. You can see that the forward adapter has been attached to the LOX tank, and we already have the liquid hydrogen tank ready to go. Next slide, please. I should mention also that the second core stage is coming together a lot faster than the first, which is good. We've worked out a lot of the factory problems. So for Artemis 3, we already have our boosters ready. We're working on our third universal stage adapter. I'm sorry, not third universal. We're working on the LVSA, but what's new to Block 1B, we'll have a universal stage adapter, which will adapt the exploration upper stage to Orion. And within there, we can carry about 10 tons of co-manifested payload. We've done manufacturing demonstration articles, and things look really good there. We've already started building the EUS interstage, which is the adapter from the core stage to the EUS. We've done development articles there, and things are looking really good. We already have the first flight set for the RL-10s, which is good. We're working on Artemis 4 engines right now, I believe. And Artemis 3, I believe they're already, Artemis 3 RS-25s for the core stage are ready to go. They're still processing a few, but as you can see there, 2 are ready to go and 2 are in process. And then we're also making progress toward Bole. Bole is our follow-on booster for Block 2. Block 2 is what you're going to fly on for the Artemis or for the Interstellar probe. And so the next slide will get more into our Bole development. Bole is our new booster that will replace our current P-band boosters that we have on. Well, I guess it'll be after this one. My apologies. RS-25 production has been restarted. So we had 4 flight sets of the RS-25s that were carried over from the shuttle program. Those we would run out of those if we didn't build new ones. We're not planning on recovering them. So we actually restarted the production line for the RS-25s. After 16 years of being down, the production line is back up and operational, and we're producing nozzles and power heads once again. And one thing I should point out, we are focused on cost savings here. I think they've reduced the cost about 30 to 40% on that engine, which is an achievement in upon itself. Next slide, please. There we go. So here are the activities surrounding the Bully booster. The segments themselves are actually, the cases are composite material. You see that we're actually building the composite material there on the mandrel, where they actually are laying up the strands, composite strands in the pattern that they need to have in order to take the loads for flight. One interesting neat feature of that is that there's a helical design attribute that we are incorporating to make sure that it doesn't expand too much and put undue load onto the core stage. Sorry. In terms of our forward and aft dome, we've already performed the machining there. The ring connectors are already in the process of being produced, and also we've done subscale motor tests. So Bully is moving along. We're moving toward our first demonstration motor, and this motor, I mentioned before that the old boosters were 3.5 million pounds of thrust. These will be close to 4 million pounds of thrust per booster. So this will add quite a bit of performance to the SLS moving forward. Next slide. And Ralph asked me to bring any new information relative to the Interstellar probe forward. Over the summer, we performed an encapsulation study for the Interstellar probe for both configurations using a CASTOR 30 and a CENTAUR. That's mislabeled. It's really a CENTAUR 3, not a CENTAUR 5. CENTAUR 5 is what flies on Vulcan. But what we found is that there's no major disconnects. There's nothing that would stop us from integrating this vehicle. There are some forward work items relative to the handling of the RTGs, whether it be during the encapsulation process or in the VAB. And also we found that there's a limitation that popped up recently with the ML2, our second mobile launcher that will fly the Block 1B and Block 2 vehicle, relative to having cryogenic payloads. We had written a requirement set for the second mobile launcher to include the capability to have cryogenic payloads, but apparently with as the design has moved forward, the real estate that the hardware would take up has been evaporating recently. So it'll take some development effort to bring that back on the table. Not to say that it can't, but there's going to be some dollars involved with bringing that capability back online. For the next slide, you can see we have our short fairing. When we assess the CASTOR with the Interstellar probe and Star 48 all stacked together in our short fairing, we noticed that the RTG doors, which we used very large RTG doors, I think they're comparable to the size that was used for Mars 2020. These doors fall just outside of our door maps that we had for the fairing, and the problem that we have here is that the door actually overlaps where we have our bonded joint between the ogive shape and our cylindrical section for the fairing. It's not that this is a showstopper. We could make it longer. We might have to do a different set of qual tests to ensure that you can put a door in that location, maybe beef up the local structure, but there would be some work involved if we needed to go this route. Next slide. If we had a 90-foot fairing, the CENTAUR 3 fits nicely within this stack, and you can see that those doors fit nicely within our door maps for the fairing. So no problems there. Next slide. We performed an assessment with our counterparts down at KSC, trying to figure out what would be required for accommodating RTGs during on-pad operations. In the VAB, we would require a clean room to access the fairing, to be able to get in and do the operations necessary to bolt the RTG onto the spacecraft. I believe you can see the picture here. This is for our current pair, which we call our payload environment access room. It's a bit smaller than we had anticipated. Well, we thought would be necessary for an RTG. And so as a non-standard service going forward, a larger room would need to be crafted. It's not that we don't have the capability, it's just there would be money involved to go make that happen. And also we've assessed the areas in the VAB where we could access and control the RTG integration. And what I mean by that is the RTG itself is controlled by the Department of Energy, and there would be restricted zones in the VAB while we're undergoing the integration operations of the RTG. And just make sure I cover the bases. I should point out for the short fairing, I'll get into the slide here, but the short fairing, we can accommodate a hot fit check of the RTG down at the PHSF. That's not a problem. When we start encapsulating a 90-foot fairing, we would need a separate facility to do that encapsulation. And I believe the EPF, the Eastern Processing Facility, can accommodate the 90-foot fairing, although that facility is not certified yet for the handling of RTG. So that would be forward work. Next slide, please. Thank you. Thank you, Kirby. All right, so benefits of flying on SLS. I think I've shown this before at multiple meetings, but SLS offers the unrivaled mass. It really does have benign launch loads. We have the data to prove it. We can provide ultra high departure energy, which the Interstellar probe is seeking. We have very large diameter fairings, which gives quite a bit of flexibility. And we have a heritage of success with these systems. It's also worth noting that we are human rated, and that comes with additional margin and reliability of that rocket, that system that could be capitalized on. And all these capabilities really roll up into overall mission flexibility, bigger science, the more things you can do. And so ultimately, this really provides a greater return on your science, lower mission costs, reduced risk, and we're ultimately gearing toward exploration. We're trying to make the impossible possible and trying to help you solve the mysteries of the universe. So with that, thank you for allowing me to come forward and present where we are with SLS and our current progress. And are there any questions?
Thank you, Rob, very much for the update. It's exciting to see all those pieces coming together, and I can't wait to see launch come around. We do have one question in the chat here from Tom Comegis. He says, is there a projected launch date for Artemis 1? I don't know if that's been announced, given the recent changes in the schedule or not.
The current launch date, they're quoting launch period 16, which is between December 20th and January 3rd. I think that might slip a month or two. There's some debate what should happen there. I think we're on the verge of the slip, and so that word might come out in about a week or two. And if it does slip, I don't think it's going to go any further beyond March, but hopefully by February we can get this bird off the ground.
Thanks, Rob. It must be nerve-wracking to see so close to the end, that end in sight, so to speak, or the beginning in sight, being the first launch. And though it's been going on for years, these months must feel like whole new years to themselves. So.
Well, they are. There's a monumental amount of work going on right now just to get us to flight. And what's also frustrating and unfortunate is everything that surrounds COVID-19. And we've had a slowdown. We've lost people on the EGS, the ground side, trying to put this rocket together. It's sad. It's very sobering. But we're trying to do the best job we can moving forward.
Wow. Well. Hopefully we'll get to launch soon, and it'll be good to see that. So we have a question from one of the students who's been joining us all week from Nibbin. He says, congrats on the new iOS SS water deluge system and protecting onboard payloads and equipment. How about CubeSats in the adapter? Are they deployed by ferrying? By the fairing?
So what I should point out there, for Artemis 1, we have our CubeSats integrated into our Orion stage adapter. Once Orion separates, there's a big hole that's there at the top of the vehicle where the CubeSats can deploy through. So our deployment systems shoot them out through that hole. Thank you. You can sort of see the deployers here. They throw the CubeSat straight along their longitudinal axis here, and down on the lower right, you can see how they're sort of aimed, if you will, toward the center of the vehicle where they can shoot straight through that Orion's. There's a stage adapter that Orion has that it's resting on. You can't see it when it's encapsulated with the encapsulation panels, but once Orion separates, moves away, you can shoot them through.
So that means that these CubeSats will be on the trajectory that Orion has been put on, the translunar insertion orbit. And so this stage puts Orion on that trajectory, and then Orion separates. Right. And then these CubeSats are now on the lunar trajectory, and they simply separate from the second stage as well, or the third stage.
Yes, this would be our third stage. That's right.
Yeah. So very cool. So that's a marginal amount of mass added to that uppermost stage to get 6 payloads out to the moon. That's fantastic. So very cool. And let's see. We've got time for a couple more questions. If folks have more questions for Rob, I know that actually, Rob, I can't remember. Are you hopeful that you'll be at the American Geophysical Union meeting with more information on SLS in December? Because I know that you've joined us there in the past. Some of your team has as well at AGU, and they're still planning on being in person. So,
well, that's great news. I'm hopeful that I can be there in person, and also if I can be there in person, I hope we can set up a tour of MAF. If we're going to be at New Orleans, the Michoud Assembly Facility is a short drive away, so that would be great for some of our stakeholders in the science community to come see what we're doing. Yeah. That
would be great. Let's follow up on that. I think you might have mentioned it earlier. One of the questions that I've got is after Artemis 1 flies, what is the schedule for the second Artemis flight?
That's a good question. As I said, we already have hardware in place. I think we're not limited by the SLS hardware in this case. We're more limited by what Orion needs to do. Orion's planning on taking the information that they've learned from flight for Artemis 1 and incorporating it into their flight software design. They're going to make some modifications to their flight software. And I hear it's going to be nearly 2 years before they can fly again. That might be shortened. They're looking at ways of bringing that part of the schedule to the left. And so we shall see. I think we originally planned for Artemis 2 being in 2023 timeframe. It I believe might push out to 2024, but I think by 2023 we'll have Artemis 2 under our belts. So.
And of course you and I will be on a panel at the symposium run by the American Astronautical, not astronomical. The American Astronautical Society down in Huntsville in a couple of weeks, talking about specifically science on SLS, and so that's really exciting. I'm looking forward to that. So,
yes, and thank you for supporting.
Yeah, you bet. All right, so we are up at 1 o'clock. Rob, thank you very much. Really appreciate you being here, and look forward to more good news out of SLS as the rocket continues to come together and we get closer to launch. And thanks for all your support along the way. This has been fantastic.
Oh, I'm happy to be a part of it. And again, I think we're going to set some records with this mission. All right,
absolutely.
Take care.
Fantastic. Thank you.